And there's the answers for the bell work right there. Hopefully you got the same answers. And here's our objective for today. I can find the surface area of a pyramid. Just take 30 seconds to copy that down, please. All right, how do you name prisms? By the shape of the base. So kind of like some of these what we've seen. I guess this would be a rectangular type right here. All right, so you just take that shape. So you can I guess copy it down like this, at least if you're drawing it by hand like I am. And you just kind of connect those lines this way. Of course, some people like to they draw this in the front here like this. Well, they draw it better than I do, by the way, but that's a different story. And just so that I can connect these lines, I got to separate them a little bit farther. Then they connect the lines this way. It doesn't really matter. I mean, it's still a prism of some sort. But it takes the name. The name is the shape of the base. So like this one, I'd say the base generally is like the top and bottom. So the top is this top surface. And the bottom is this surface right here, which are, in this case, I would say rectangles. And you could say the same thing on this other one. And with rectangular prisms, it's a little bit more difficult to name. Not, I guess, more difficult, but maybe more difficult to figure out which is the base. Because you could say, well, all the sides are rectangles. That's true. The lateral area is also made up of rectangles. So like on this one, you could say the lateral area is going around up and down like this. Okay? So perhaps it'd be easier with a different shape, like, I don't know, a triangle like this one, right? And so this is something that we've been seeing with prisms, is that the lateral areas are all made up of rectangles. Okay? So on this one, we would see very clearly that the base on this one would be these two triangles, rather. So we would say that is a triangular prism. And then these other two we did before, those are rectangular prisms. I think we should address that. Let me see if I can, there we go. So I copied this so I can mess with it a little bit. Let's see if I can lock this down just a little bit. Okay, so let's take this shape then, this one right here. And it's weird that it's kind of open on some parts of it. Let's move it over here actually. So I'm going to take this shape and I'm going to rotate it like this, right? So now it's kind of saying, and you could, I guess, say that this rectangle right here is the base. Now, remember that the lateral areas of a prism specifically are all rectangles. So really what we kind of want to do when we want to name a prism is look for the shapes that are different than rectangles. Now, of course, if it's a rectangular prism, that's difficult to do like we saw in these first two examples, which is why I made this triangular one. But you'd say, well, that's a rectangle, right? And then we see that it's connected by all these other, this green rectangle right here, and then we'll say this red one right up in here. So those three are all rectangles. So what's the different shape? It's clearly the triangle. So that would have to be a triangular prism. Now you may be wondering, well, why did we talk about prisms when today's objective is about pyramids? There's a reason. We'll get into that. So just giving the name of each of these prisms right here. Yeah, so this one here in the top left, we'll start with this one, 7 by 12 by 6 prism. Again, you're looking for the shape that's non-rectangular. And I would see that this one only has rectangles, which would mean that this one is a rectangular prism. Or this prism right here, again, just looking for any non-rectangular shapes, and, well, I found one right there. See if I can, boom, I found it. This one, right? So this is a triangular prism. Or in the bottom left, I see this different shape. It's definitely not a rectangle. Just throw it away. That is a 5-sided shape, which is Pentagonal Prism. I'll write the names of these on the next one as well. Next slide. And so that's Pentagonal Prism, but what about this one is a blue shape right here. Again, the shape that I see that's different is a 6-sided shape, which is a hexagon. So we would say that's a hexagonal prism. When you're looking at prisms, or really any base that's non-triangular or rectangular, because they're kind of weird shapes. We're looking for that word they used in the last assignment, which is called the apothem. So the apothem is when you go to the middle of the shape, and I'm going to pretend like this is the middle of that hexagon right there. And it creates a 90-degree angle with any of the sides, which is why in that last assignment we kind of saw these, sometimes it was dashed line, hopefully it's a straighter line than mine. But then it shows that it creates a 90-degree angle with that box of the edge of that shape. Okay, and again, that's important because it tells us that the height of that triangle, and yeah, actually it's the same, even though again this may look slightly different, but it's the same 90-degree in length for all of those triangles, right? So if we connected these, get six triangles like this. So how's a pyramid different than a prism? Yes, so the lateral areas now for pyramids are going to be triangles. There's only one base. So how do you name pyramids? It's still by the base though. Yeah, a pyramid has triangular slanted faces that meet at a point. A prism has rectangular side faces. This is the difference. And yes, again, prisms have two bases, whereas pyramids have one. But again, we're still naming it by the base. So let's look at a relationship between a pyramid and a prism, just like we saw in those last examples. All right, so this one we just saw on that last slide, right? And this is a prism, of course, because it has a rectangular lateral surfaces on that. All right, now, as it turns out, pyramids are actually made from prisms, like this one, okay? So I'm going to say that that the bottom part is the base. That's this bottom base right here. That's a pentagon, again, right? Now what we do is, and it is very comparable to a prism, which we're going to need to know in order to find the, well, I guess that'd be volume, but surface area is a little different. So what this does is it actually comes up into the middle of that top base part, which is in this case pentagon. And it always meets at a point, just like it says they meet at a point there on number 3. And what it does is it just kind of creates lines down. In fact, I'll try to do this electronically so it looks pretty. It creates lines from that point to these other vertices of the original, okay? Now those aren't very thick lines, but I hope you can see that okay. Now I can clean this up, right? I can say, oh, let's look at this. Clean this up so it looks a little bit more pyramidish. Okay? And so now this would be a pyramid, and it is related, right? But now we can see also, especially if we zoom in, and if I had not erased all the lines, that we have only triangles on each of the edges, right? Here, 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 and so forth. Now, the last thing I'm going to say about pyramids is these triangles that we create on the sides. We're not going to do anything funky with these triangles, meaning that all the triangles should be the same size. If they're different sizes, they're going to have to tell us that, okay? But if they don't, then we get to assume that they're all the same size triangles. Now, this also brings up the case of the net, okay? Like this pyramid that we've just drawn, not knowing any of the lengths. The base, of course, would be a pentagon, like this one. Well, it should be better, but that's about as good as I can do it. And so if you were to make a net on this thing, you'd have triangles all the way around, okay? Like this one, and this one, and this one, and this one, okay? And then, of course, you're saying, well, how many triangles are there? And they're all the same size. So if you can just figure out the area of one of these triangles, for a pentagon, you'd multiply by 5. If it were some kind of rectangular, really it should be a square pyramid. Then you'd be multiplying by 4. If it were triangular, you'd be multiplying by 3. And then, of course, you can go up in the numbers, hexagons and nonagons and things like that, okay? But we shouldn't say anything more than a hexagon. Today's lesson, of course, is specifically about surface area, so the net, it may be useful for you to draw that out. So let's just start by naming these pyramids. Now remember, all the lateral parts are triangles. But the names of these, okay? Now if it's like this one right here, of course we see that all of the faces of this shape, all the surfaces of the shape are all triangles. So again, that may seem like it's indeterminate, but this one would be a triangular prism right here. Yes, I meant pyramid. I almost said prism again, actually. But pyramid, these are all pyramids, of course. I apologize. Got prisms on the mind, I guess. Yes, this is a triangular pyramid. And again, I would be looking at this as the base. But depending on which values they give you, you'll have to make that determination, okay? So if I look at this top left one, and you could say that's a square. I mean, it just depends on your perspective. I'm just going to say that it's a rectangle. So we'll call it a rectangular pyramid. Again, you're okay to call it a square pyramid if you'd like. Right here, how many shapes is that bottom? The base, 1, 2, 3, 4, 5, 6. 6 sides, that's hexagon. That's a hexagonal base, so this is a hexagonal pyramid. And then this last shape right here, 1, 2, 3, 4, 5. 5 sides to that polygon makes that a pentagon. So that's a pentagonal pyramid. Boom, there we go. So find the surface area of this pyramid. All right. So let's see. Again, the base, makes a difference. Yep. I would say on this one that this triangle right here is the base. And again, this is meant to be drawn three-dimensional. So it may take a little bit for your eyes to adjust and see, well, how is that really meant to be three-dimensional? The dashed lines means that they're covered up by the front of the shape. But we need to show those so you can understand that there's no funny business going on back there, okay? So this triangle, I'm just going to draw it separately. And again, this is just one method for doing this. And then if I can just figure out the dimensions of this triangle, particularly the height and the base, then I can find the area of that base triangle. So it says, I'm looking at this part right here, it's 3 miles. Now it does show this length right here is 3 miles as well. I mean, you could put that down right there. For me, it would be in the top left, I guess, the way I have it set up. But that's not really going to help us because the red dashed line goes, I'm going to show from the tip here. It shows this 90-degree angle. And that length or height of this triangle is 2.6 miles, which is shown right here. Okay? So that's all the information I need. And again, I don't really need this 3 miles. I mean, you're welcome to keep it there if you'd like, but I don't want that 3 miles to be confused with the base of the 3 miles right there, okay? So I do need the area of this green triangle right here, this area. And to find the area of a triangle, you take the base, which is the 3. The height is 2.6 miles. And we just need to divide this by 2. So I'm going to go straight to my calculator and do this. 3 times 2.6 divided by 2. And I get 3.9. And again, this would be in square miles. But I don't really need to label it yet. I just want to label the answer. So I'm going to wait to label this. Okay? Now, they've only shown one of the heights of these lateral triangles. Okay? And they don't really need to show any more because see how they've even specified that each of the lengths of this green triangle are all 3 miles? So it's a regular triangle. Yeah, it's an equilateral triangle. There we go. Not that that matters yet, but eventually will. So this equilateral triangle is important because it's going to make all of these triangles on the lateral part the same area. So all I really need to do is figure out the area of one of them. And the one that it's showing me really with the height is this one right here. Okay, so again, I'm going to draw it away from the shape so that we can see it on a separate plane right here. Something like this. And again, the base of it still shows at 3 miles. It's the same 3 miles that we used before. And then the height of this thing, it's showing at, even the arrow right there, 4.1 miles. All right, so I need the area of that purple triangle, which would be 3 times 4.1. But I need to divide it by 2 because it's a triangle. So 3 times 4.1 divided by 2, and I get 6.15. 6.15, again, that'd be square miles. Now, the next thing we need to understand is that that's only one of those lateral triangles. But how many of them were there? There's this other one right there. That's 2 and 3 right there. Yep. And we should expect there to be 3 because it's a triangular pyramid. So I'm going to take that 6.15 and multiply it by 3. What did that give me? 18.45. Now that's just the lateral parts of this pyramid. I still need to add the original base triangle, which was 3.9 square miles. So add 3.9. I get a total of 22.35 square miles. I'll address that. This is in square miles. It is surface area specifically. That's what it said up here. And we need to remember that surface area is just area. Sometimes we get these three-dimensional shapes mixed up with volume, okay? And it's very crucial not to, so that when we label these, we know exactly what we're labeling. But yeah, we only consider 2 dimensions of each of these triangles. Miles and miles, that's 2 dimensionals, or square miles. And then the bottom one, the base one, was miles and miles. Now, if you start multiplying by a 3rd dimension, that's when you get volume. But we haven't covered that yet. We will. All right. Now, again, this one, well, this is not a regular quadrilateral there at the base. That's rectangular, okay? Now, the reason I'm pointing that out is because this triangle here on the lateral face is the same as its opposite, but it is not the same as this one right here, okay, which is the same as this opposite. So actually, we're going to have to find those 2 different areas, and then we'll multiply those by 2 and add them together to figure out the area of, I guess we can call it the lateral area. Now, once again, they're showing the height of these triangles, and it is slanted because it's right on the surface of this triangle. But again, they have to give us 2. They have to give us 2 of those because they're different triangles. Okay. Now you can start with those triangles if you'd like, but for me, I'm going to start with the base. Right here, this rectangle. So again, I'm going to draw it separately here on the side, and it's a 6 foot by 8 foot rectangle. So its area is 6 times 8, which is 48 square feet. And again, I don't really need to label that yet. I will in the end when I finish and find the total surface area, but I'm just going to put that aside for now, okay? And for me, I'm going to start with this triangle right here. Now again, I know there's 2 of them, but I only really need to figure out one of them because it's duplicated on the back side. So yeah, you got the green, you got the red, it's dashed line, something like that. Hopefully yours are straighter than mine, but whatever. And this is 8 feet there on the bottom, right here. And then this red line shows it's 8.5 feet. So if I want the area, I'm just going to show this is green, the area of this green triangle here. I'd have to take the base, 8, and then the height, 8.5, multiply those, but then divide by 2. Well, what does my calculator give you? 8.5, 34. Now again, it's important to understand that's just one of those triangles. I still need the back one, which is going to be part of our total surface area. So I'm going to multiply the 34 by 2, and that gives me a total of 68 square feet from the 2 green, not that I colored the other one green, but they would be the 2 green triangles on this one. Just give myself a little bit more extra space here. Now on the left, this one right here in purple, again, I'm going to draw it separately, just knowing that there's 2 of them, right? And at the bottom right there, it shows it's 6 feet. Yeah, this one shows a height here. That's this 8.9 feet right there. So if I want the area of this purple triangle, again, I know there's 2 of them, so I need to factor that in the end. I'm going to take the base, which is 6, and multiply it by the height, 8.9, and just divide that by 2. 8.9, 26.7. I get. But there's 2 of them, so I'm going to multiply that by 2, which is 53.4. Now, some of you may be wondering, and you may have noticed this as well, well, why divide by 2 when you know you're going to just multiply by 2? That's fine as long as you understand that you don't need to multiply the 6 times 8.9 times 2. If you just don't divide by 2, as long as you know there's just the 2 triangles, that's fine. Just don't do it twice because that's a common mistake. So I kind of like to go through all the steps on this one just to see what the actual area was and then know that there's 2 of them. Because on this rectangular pyramid, of course, the opposites are the same. But when you get into bigger shapes like pentagons and hexagons, then knowing what to multiply that by can change, okay? So yeah, even though this number right now is 2 for both the green and purple, that may change. That may change, all right? So we actually figured out all 5 surfaces areas, right? We got the rectangle at the bottom, we got the 2 purple triangles, and we got the 2 green triangles, 68. So I just need to add these together. And whatever this is would be my final total surface area. Let's see what we get. 68 plus 53.4 plus 0.8, 169.4. Oh. 169.4. But the answer is not 169.4. Remember that you need to label it in this case, square feet. So find the surface area of this pyramid. And yeah, we're looking at a hexagonal pyramid because the base has 6 sides. Now, that's not too bad. This actually looks worse, I think, than it is. Yeah. Particularly because, again, all of the 6 triangles around the edges here that make the pyramid are all the same size. So really, all I got to do is find the area of the base, which is made of 6 triangles as well. And then figure that out. And then one of these triangles, just multiply that by 6 to find the full area of that part of the pyramid. The pointy part is what I guess. That's not technical, but that's what I'm going to call it. Now, I mentioned this before. This is this part showing from the center of that hexagon to the edge there. It shows 90 degrees. It's kind of like mixed with the other 90 degrees, but there's one 90-degree angle there for that length. That's called the apothem. And you won't be really tested on that vocabulary. And in fact, I don't really use it very often, but there's other classes where they use it quite a bit. They'll say apothem, 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 and I don't know that it really makes it sound smart. It's one of those weird words that I don't really know if it makes it sound smart, but we use it as math people. All right, now I'm going to acknowledge that we have a hexagon as the base on this one, and I do need some space. So I'm going to draw my hexagon. It'll be a little bit smaller, well, probably a lot smaller actually, but I just need a hexagon so I can figure out the area of that hexagon, okay? And I see that one of the lengths, and they're all the same length on the edges of that hexagon, they're all 7 centimeters, like this. Okay, so that's 7 centimeters, and we even see the markings. We've talked about that before. See all the markings? It's all one mark on each of the edges of that hexagon, which indicate that they are the same length. Or congruent. That's another fancy word. Also, they've shown us from the center of that hexagon to the edge, it's 90 degrees. That's the apothem. That shows that 6.1 centimeters. So we do need that value, 6.1 centimeters, because we're going to make a triangle right there. Okay. Now I need to find the area of that green triangle first. And the area of that green triangle, I see it's a 7 by 6.1 triangle, 7 base, 6.1 height. I do need to divide that by 2 because it is a triangle though. So 7 times 6.1, all divided by 2. That gives me 21.35. That'd be square centimeters. I'll wait to label it though. And again, the reason why all of these lengths are the same for this hexagon is so that we can actually split this up into all equal triangles. So from here, we just say, well, how many of these triangles that we started with, how many are there? 1, 2, 3, 4, 5, 6. 6 triangles, just like we would expect from a hexagon that has 6 sides, should have 6 triangles. So I'm going to take the 21.35 and multiply it by 6. I'm just going to use a calculator, but you don't have to. I get 128.1 square centimeters. Okay, now again, I need to know that that's the area of the full pentagon right there, 128.1. Okay? And that may have felt like a lot of work right there, but we're not finished. We still have, yeah, I know, right? That sounded like a what, like, of course we're not. We need more work to do. It's so fun. So I'm gonna I'm gonna do this. I made it blue right here, even though that's an ugly color. It's kind of disgusting. But I know that the base of this blue triangle right here is just the same length as the edges of that hexagon. It's 7 centimeters. And the red line, which is kind of on this one right here, but it's still the same height of that triangle, it shows is 10 centimeters. Now I'm just going to find the area of one of those blue triangles. Again, some of you may combine that all at the same time right now, which would be fine. So that is the base is 7, that's 7 centimeters, not 70 meters. 7 times 10 centimeters, but again, I need to divide that by 2, 35 square centimeters. And again, we just need to acknowledge that there's 6 of those triangles, right? I did this one, but that's 1, 2, 3, 4, 5, 6. There's 6 of those, so I need to multiply 35 by 6, and that will give me the total surface area from those triangles, and you can call it the lateral, but just the slanted ones. 35 times 6 is 210. But we still have the area of the hexagon right there, the 128.1. So we're just adding these together. That will give us the total surface area. What is that? 1, 8, 3, and 3. 338.1. But the answer is not 338.1. It is 338.1 square centimeters. Just don't forget your labels. Well, there's our objective again. I can find the surface area of a pyramid.